Hello and welcome to part 4 of UV visible spectroscopy. I'm Sarita, Assistant Professor of Chemistry from GDCW Begumpet. So in our last class, we have completed the Woodward-Fieser rules. What is the base values for that is enes, dienes, trienes, and then even enones, that is alpha, beta unsaturated carbonyl compounds and aromatic compounds. And what are the increments that have to be given for those groups when they are present at various positions, that is alpha, beta, gamma, delta. And if you are taking aromatic groups, then based on the position of the substituents which are attached to that ring, that is whether it is attached to ortho, meta, para. So we have seen 2 examples in our last class. So we'll continue with the examples. How to calculate the lambda max values of these compounds. So just the example what we have completed was this. So this is nothing but a conjugated diene, and as the double bonds are present in 2 different rings, so it is a heteroannular diene. So first the heteroannular diene, the base value is 215 nanometers. Then what else it contains? So it contains ring residues also. What are ring residues now? The sp2 carbon, the carbon which is present here is part of this ring. So it is having one ring residue. Another sp2 carbon here is also a part of this ring. This is another ring residue. Then the third, this carbon is also having a ring residue. So total there are 3 ring residues. And for each ring residue, what is the increment that has to be given? It is 5 nanometers. So as there are 3 ring residues, what will be the increment that has to be added? So it will be 3 into 5. That means 15 nanometers. Now, it is also having one exocyclic double bond. Now this bond, if you look at this bond, so this is the structure of, this is the ring, and this is the double bond which is exocyclic to this ring. So it contains one exocyclic double bond where the increment is 5 nanometers. So calculated value will be 235, and the observed value was also found to be 235 nanometers. Then example 2, again here it is a conjugated diene system, but both the double bonds are present in the same ring. So it is a homoannular diene, and the base value of homoannular diene is 253 nanometers. And there are 2 ring residues. So this is one ring residue, this is another one. So 2 into 5, it is 10. It is also having 2 alkyl substituents. This is alkyl substituent, and this is also another alkyl substituents. So again, for alkyl substituents, for each alkyl substituent, it is 5 increment. So 2 alkyl substituents means it is 2 into 5, which is 10 nanometers. And if we add all these 3 values, we'll get 273, and the observed value was found to be 263. Now, next example. This is also again a diene. This part you can see double bond, single bond, double bond. Okay, but how is this diene? It is not present in a ring. So we call this as a cyclic conjugated diene. So for a cyclic conjugated diene, the base value is 215 nanometers. So that's why we will be taking this system as a cyclic conjugated diene having 215 nanometers. Then at this carbon, this is the alkyl group which is attached. So it is one alkyl substituent. Here also you can see this is another alkyl substituent. Then at this carbon, this is ring residue, and this side also one ring residue. So there are 2 ring residues, and these are 2 alkyl substituents. So what we have to do, for each substituent, whether it may be ring residue or alkyl substituent, the increment is 5. So 2 ring residues, so 2 into 5, it is 10, as well as 2 alkyl substituents, So 2 into 5, 10. Now we have to see what else is present in this compound. So we also have this double bond. If you look at this carefully, this is present, that is, it is outside the ring. That means it is actually an exocyclic double bond. So you can see the double bond which is present outside this ring. So we can consider this as exocyclic double bond, which is again the increment of 5 nanometers. So what it is having, first thing is it is an cyclic conjugated diene with 215 nanometers as the base value. There are 2 ring residues, 2 alkyl substituents and 1 exocyclic double bond. So total, if we calculate, we will get 240 nanometers. Now you look at this example. Now what is this system? It is again a conjugated diene. Now whether it is homoannular or heteroannular. So for that, look at the double bonds, how they are placed. One double bond is in one ring, the another double bond is present in another ring. That means they are heteroannular diene. So heteroannular diene base value is 215 nanometers. Then look for the ring residues. So you can see this part, when we are considering this whole part as a diene system, then this carbon, this will be one ring residue at this carbon. This is another one. Now this carbon is also a part of ring residue. Even this carbon, this is ring residue. So total, how many ring residues it is having? So it is having 4 ring residues. So 1, 2, 3, 4. So 4 ring residues. So it will be 4 into 5, which is 20 nanometers. So what else it has? Does it have any exocyclic double bond? It is not having, because you can see both this double bond, it is not present outside this ring, because it is, these 2 rings are actually separated by a single bond. So there is no exocyclic double bond. So only it is an heteroannular diene and it is having 4 ring residues. So total calculated value will be 235 nanometers and the observed value was found to be 236. Next example. Now these are simple examples again. So you can see these 2 double bonds present in the same ring. So it is, base value is 253 because it is homoannular diene. And how many ring residues it is having? This part. So this carbon, for this carbon, this is 1 ring residue. And for this carbon, this is the ring residue. Okay. So there are how many ring residues? 2 ring residues. So for each ring residue, it is 5 increment. So total 2 into 5, it is 10 nanometers. And it is not having any exocyclic. So only just 2 values, 253 plus 10, it is 263 nanometers. And the observed value was found to be 256 nanometers. Now this system, if you look at this, so here you can see the aromatic group where it is having a keto group which is attached. So what is the base value for such aromatic ring which is having a keto group? So the base value is 246 nanometers. Now you have to check for other substituents which are present on the ring. So what are the substituents which are present? It is OH group, hydroxy groups. So OH groups, what is the position where the OH group is attached with respect to this keto group? So this will be ortho position, meta, and the other is para. So there are 2 OH groups. One is at meta and the other is at para. So when OH is present at meta position, the increment that has to be given is 7 nanometers. And when the OH is at para position, it is 25 nanometers increment. So total, if we add, it will be 278 nanometers. And the observed value is 281 nanometers. Now again, what is this system now? In this example, is there any keto group? There is no keto group, there is no aldehyde group. So what is there? Only double bonds. And is it annular? It is not annular. So it is a cyclic diene, conjugated diene. So this whole part is a cyclic conjugated diene. Now what is the base value of a cyclic conjugated diene? It is 215 nanometers. And there are two ring residues. Actually, we should call this as alkyl substituent. Where are they? Here. At this carbon, this is the alkyl group. And at this carbon, this whole thing is the alkyl group. So there are only two alkyl groups. So for each increment is 5. So it is 2 into 5, which is 10 nanometers. So total, the calculated lambda max will be 225 nanometers. Now this example also the same thing. It is again a cyclic conjugated diene. Okay, so a cyclic conjugated diene. What is the base value? Again 215. So this part, it is trans, actually S trans. So this part is conjugated diene. And these are the one alkyl substituent. This is another alkyl substituent. So two alkyl substituents are present. So 2 into 5 is 10. Total will be 225. Calculated lambda max is 225 nanometers. Now next example. Now here it is a enone, double bond, single bond and carbonyl. Now this is alpha carbon and this is beta carbon. With respect to the carbonyl, we have to check. This is the carbonyl group. So the double bond which is attached to this here, this is the alpha position and this is the beta position. Now it is a conjugated enone. So what is the, and it is acyclic. It is not a part of a ring also. So it is acyclic enone with the base value of 215 nanometers. And there are ring alkyl substituents. So at this carbon, you can see this is one alkyl substituent and this is another one. So there are two alkyl substituents which are attached to the, which position is this? This is beta position. This is alpha. Okay, then this will be beta. So there are two alkyl substituents at the beta position. So for each alkyl substitution at beta position, the increment is 12. So as there are two alkyl substituents, it is 2 into 12. That means it is 24. And the total calculated lambda max is 239 nanometers. And in the next example, again, it is a aromatic system. The same thing we have covered. Hydroxy groups at meta as well as para position. So by taking the values, the same thing we'll get as 278. Now we have seen how to calculate the lambda max of enones, then that is conjugated dienes and aromatic compounds. Now if we have a if we have a double bond conjugated diene system, but where there are more than 4 double bonds which are in conjugation, that is we call it as polyene. So for such compounds, we need to follow Fieser-Kuhn rule. So Woodward-Fieser rules are only for the conjugated diene and triene system. If it is a polyene system, another scientist named Kuhn, he has framed some rules which are now, we call them as Woodward-Kuhn rules, or that is Fieser-Kuhn rules. So they have given a formula for calculating the lambda value of such polyenes. So how to calculate them is lambda max is equal to 114 plus 5m plus n into 48 minus 1.7 n minus 16.5 into R endo minus 10 R exo. Now what are these M, N and R endo, R exo? So here in the formula, M is nothing but number of alkyl substituents. So it gives, that is, we have to count the number of alkyl substituents which are present in the compound and then substitute that value here. Then what is N? Actually, it should be small n here. It is number of conjugated double bonds. So N is number of conjugated double bonds. R endo means number of rings with endocyclic double bonds. And R exo is number of rings with exocyclic double bonds. So endo means here endocyclic. Exo is for number of rings with exocyclic bonds. So by taking this, that is the formula, we can calculate the lambda max of some polyenes. So first we'll take this example. So now in this, first count how many alkyl substituents are there. So in this, there are 10 alkyl substituents. So where are the alkyl substituents? You can see all the methyl groups are alkyl substituents here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So total 10 alkyl substituents are there. Now how many conjugated double bonds are there? So how many conjugated double bonds are there? So all the double bonds which are in conjugation we need to add. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So total it is having 11 conjugated double bonds. Then how many rings are there with endocyclic double bonds? So endo means the double bond which is present inside the ring. So in this double bond is present inside the ring. This is one endocyclic double bond here. And in the other ring also there is one endocyclic double bond. So there are 2 endocyclic double bonds. Now what we have to do, we have to substitute all the values in the formula. So 114 plus 5 into 10. So 10 is what? Number of alkyl substituents plus N is 11. N is what? N is the number of conjugated double bonds. Then 48 minus 1.7 into N. So N is again 11 here minus 16.5 into R endo. That means number of double bonds having a number of rings having endocyclic double bonds. So there are 2. So we have taken 2 here minus 10 into R exo. There is no exocyclic, so it is 0. So if you calculate this, you will get lambda max as 453.3 nanometers. So this is how, by substituting the values of M, N, R exo and R endo, we can calculate the lambda max value of polyene by using this formula. In the next example again, you can see the number of alkyl substituents are 8. So 1, this is all alkyl substituent. So 1, 2, 3, 4, 5, 6, 7, 8. This is actually, it is taken as diene system. So when we are taking conjugated double bonds, so here there is no conjugation. Just check here. There is no conjugation. Okay, till here we have conjugation. So 1, 2, 3, 4, 5, 6, 7 and 8. So this part, just look carefully, you will find till here, from here to here, this part, it is conjugated. Whereas this double bond is not in conjugation with this, okay, because it is separated by 1, 2, 3 single bonds. Even this double bond which is at the terminal, this is also not in conjugation with this part. So here also you can see it is separated by 3 single bonds. So when you are considering the alkyl substituents or conjugated double bonds, we need to be very careful. First look at the structure and then first find out the conjugated system. So number of alkyl substituents are 8 and the conjugated double bonds are 11. Then if we substitute the values, so 114 plus 5 into 8 plus 11, that is 11 are conjugated double bonds. Then what it is, 48 minus 1.7 into n is again 11, minus 0 minus 0, that is we don't have R endo and R exo, both are 0. So complete thing is 0 here. And if we calculate that, we will get lambda max at 476 nanometers. Then now what is this system? Now this is again a diene. Okay, so diene, and whether it is homoannular, acyclic or heteroannular. So it is a hetero or homo. It is not a part of the ring, isn't it? So the base value, it is acyclic diene with base value 215 nanometers. Okay, this is acyclic and it is having exo double bond, because this double bond, if you look at this, it is present outside to this ring. So we call this as exocyclic double bond. And there are 2 ring residues. Where are they? At this carbon, this is 1 ring residue and here it is another ring residue. So there are 2 ring residues. So what we have to do, 2 into 5, that is 10 nanometers. So total we have to add, so it will be around 230 nanometers. So lambda max for this compound will be 230 nanometers. So this is how we have to first find out the basic parent group, that is whether it belongs to a conjugated diene or alpha beta unsaturated carbonyl, or whether it belongs to a aromatic compound. Then after that, whether it is having alkyl substituents or ring residues, and then if it is having exocyclic double bonds, we have to give the increments accordingly. So these are some of the examples we have covered, how to calculate the lambda max of some compounds by using Woodward-Fieser rules. So the overall applications of UV visible spectroscopy are, we can use it in qualitative and quantitative analysis. So qualitative is the nature of the group which is present in the compound, and quantitative analysis is how much amount of the compound is present. Now how to calculate this is, we have seen in our last class about Lambert-Beer's law. So what is Lambert-Beer's law? It is A is equal to epsilon Cl. What is A in that? A is absorbance is equal to epsilon, that is molar absorptivity coefficient. C is concentration of the solution and L is the length of the path, that is path length. So by taking that as a formula and substituting the values, we can calculate the quantitative, the amount that is present in the given compound. It is used for characterizing the aromatic compounds and conjugated olefins. It can be used to find out molar concentration of the solute under study. So characterizing aromatic compounds means we can know whether actually UV visible is for finding out whether unsaturation is present or not. Then in that, if it is an aromatic compound, if it is a benzene ring, we should see the B bands, that is benzenoid bands, which are present in the UV spectra. So by looking at those B bands, we can conclude that it is an aromatic compound. And if whether it is conjugated olefin or a simple olefin, that also we can find out. If it is simple olefin, we can see the lambda max appears around 200 to 40 like that. And if it is a conjugated olefin, what happens? As there is an increase in conjugation, so the lambda max moves towards the right side. That is, it shows bathochromic shift, that is red shift. So by that also we can say whether it is a simple olefin or a conjugated olefin. And we can find out the molar concentration. So molar concentration, again by using the formula, that is A is equal to epsilon Cl, which is Lambert-Beer's law. Then detection of impurities. How can we detect impurities? By comparing the two spectra. That is, one will be already, we will be having a pure compound spectra, UV spectra, and the compound which is having impurities, even that also we have to take and then compare both the spectra. So the spectra of impure compound will have some extra bands in it. So by those extra bands, we can easily detect whether the given compound is pure or impure. So it is one of the important methods to detect the impurities in organic solvents. Then detection of isomers are also possible. So isomers generally we can take that is geometrical isomers, cis and trans isomers. So these isomers can be easily detected because they will show lambda max value at different positions. The determination of molecular weight using Beer's law. That is, A is equal to epsilon Cl. We can now determine the molecular weight of the given compound also. So these are some of the applications of UV visible. So we have completed the topic, that is all the important subtopics in this lesson. That is, we have discussed the principle behind UV visible, what are the different molecular energy levels, and how the transitions takes place when UV light is interacted with the matter. So the transitions takes place between the electronic energy levels. That is, the electronic energy levels in turn consists of rotational energy levels and that is vibrational energy levels and rotational energy levels. So that's the reason when the matter is interacted with this UV light, because of the electronic transitions, there are transitions which are taking place even in the rotational energy levels. So as the rotational energy levels are very close to each other, it appears as a band. The spectra appears as a band. So hence it is known as electronic band spectroscopy. And the different transitions, that is electronic transitions. So 6 different transitions. Sigma, we have different energy levels, that is sigma, pi, n, sigma star, pi star. So always transitions takes place from HOMO to LUMO. So what is HOMO? Highest occupied molecular orbital, to LUMO. What is LUMO? LUMO is lowest unoccupied molecular orbital. So transitions takes place from HOMO to LUMO. So what are the various compounds that show different types of transitions we have discussed? Suppose if we are taking alkanes, in alkanes we can see sigma to sigma star transitions. Then for pi to pi star, we should have that is double bonds, multiple bonds. When there are multiple bonds, we can find pi to pi star transitions. And if we are having heteroatoms, suppose if we are having carbonyl group C double bond O. So what are the transitions that are seen in such compounds? It is pi to pi star as well as N to pi star, because there are N, that is non-bonding electrons which are present on oxygen. So N to pi star transitions are also possible for carbonyl group. Then we have discussed about what is chromophore and what is oxochrome. So that is very important. Chromophore is the functional group which absorbs the UV light and it imparts color to the compound, whereas oxochrome it itself does not absorb, but when it is a part of the chromophore, when it is attached to the chromophore, then it alters the wavelength as well as the absorption intensity. Then we have seen the shifts of absorption intensities, how it changes. If the wavelength is shifted towards right side, that is, if it is shifted towards the longer wavelength, we call that shift as bathochromic shift or red shift. If the wavelength is shifted towards the left side, it is known as hypsochromic shift or blue shift. And if there is an increase in the absorption maxima, that is epsilon value, if the intensity is increased, that is known as hyperchromic. And if it is decreased, if the intensity is decreased, it is hypochromic effect or hypochromic shift. And then we have discussed about this Woodward-Fieser rules. What that is, what are the base values for homoannular, heteroannular dienes, then for enones and aromatic compounds, and the increments that has to be given for each and every substrate which is present on the ring or on a cyclic system, and some of the applications. So hope you have understood the topic. It's very simple and is very easy for you to understand also. The concept is very simple. So thank you for watching.